An array is a collection of values, usually of the same data type. So, for example, I could store 12, which is an integer in the first position, and the next one would also have to be an integer, so 54. I couldn't then have the letter B. Some languages kind of bend this rule, and the rule is kind of based on different languages, so it really depends on the language that you're using, but generally an array is considered to be of one type. What is consistent is how items in an array are accessed. They're accessed based on their position in the collection. Most arrays, most programming languages use zero indexing, which is where the first item is referenced using the number 0. Some languages like Lua and also some more mathematical languages like MATLAB will use 1 indexing, where the number 1 represents the first item. When dealing with memory, it makes a bit more sense to use 0, because otherwise that would be wasting it, but for someone like a mathematician who doesn't really care about how the memory is working, they just want to do some kind of calculation, then 1 makes a bit more sense to a human. Let's say we want to store a collection of people at a party by their name. So maybe the hosts are person A and person B. So they're going to start off already at the party. If we want to add a new person, so say someone else joins the party, person C, they can go into the next slot. Just because we have 6 available locations doesn't mean they all have to be full. So for example, these values here are sometimes considered null if they don't store a value. If we add another person, person D, null is removed from that location and it is replaced with the value D. We can do that again. E. Now F joins, and if G wants to join, we can't. We haven't got enough space. An array is stored with its values next to each other in memory. And so if we have 6 locations available, that's allocated to the array. The next point afterwards might not be available. It might be taken by another variable or another value. And so we can't just extend the size of the array. It's a static array. It doesn't change in size, because otherwise that wouldn't really make sense. If we wanted to use a static array to represent all of the people at a party, we would need to know ahead of time what the maximum amount of people that could join the party is. So let's say, for example, 6. But what if nobody turns up? That's a rather unfortunate party for A and B, who are the hosts. If no one turns up, we've wasted a lot of memory, because all of these locations have the values null. And this isn't ideal, because all of this memory is being wasted. We're just storing null. So ideally, what we want is a different type of array that can scale in size. But we can't just do that normally, because if we remove these locations from the array, then they're gone. They're gone from the array, and it's just like index 6. Which, if you remember, we can't extend the array. We can't add more items to an existing array, because there might be something else there and we don't know. So a dynamic array is a bit of an abstraction. We move a step away. We don't change the size of an actual array, but we do change the array that we use. So for example, if we have an array of size 2 and it's full, ignore these bits for now. We have an array of size 2. If we want to add another element, we can't. We haven't got enough space, we've only got 2 slots. What we can do is we can create a new array of size 6. We can copy all of the old values into the new array. So we copy the first item from the array of length 2, into this one, and the second item into here. Now we can use more items. Now we can add C to the party. And this is what a dynamic array does. It says if there aren't enough available locations in the array to add a new item, we just create a new array and copy everything over, and then we can get rid of the original array. This also works on the other side. If we've got too many null values, a dynamic array might shrink the array so we're not wasting as much memory. But this can be very slow. If we have an array of length 1000 and we need to add another element, that means we need to copy 1000 values from one array to another just to add the 1001th item. And that's quite slow, and that's not ideal. So we actually have another option available to us. The issue with the dynamic array is that we rely on the fact that all of the items are stored together. The sixth element or position, or the seventh element or index 6 of an array must be the very next memory location after number 5. And that restricts us. That means that we need to move about our memory. But what if we just said, I want to store one item and the memory address of the next item? That's what a linked list does. We store a node, it's called. We have a value and a memory address to the next location. In this case, it's usually denoted with an arrow because we can have a value here. So for example, A, and the next value after A should be B, and the next should be C, and the next should be D. And now we can add as many values as we want. We don't have a maximum capacity anymore, and we're not wasting memory by allocating more than we need. We can just add or remove the next value from the last item in the linked list. Linked lists also allow us to do insertion and deletion a lot quicker. So in an array, if we have the values A, B, C, E, and we'll leave these as null for now. If we want to add C, and we want to insert it in the right position in between the B and the D, what we need to do is we need to shift everything along. Not everything, but everything after the new location. So we want C to be right after the B. So we need to shift E along to index 4. We need to shift D along to index 3. And only then can we replace index 2 with the value of C. Insertion is quite involved. We need to shift a load of values out of the way so that we can add the new value in its place. With a linked list, we have A, B, D, and E. We can just create a new node with the value C, and we change, or rather we copy the next value from B, which is the node before C. So B currently points towards D. We copy the memory address of D, and we have C point to it. And then we take the memory address of C, and we point B towards it. So we do that, basically, with the arrows. You can also see that removing is just as easy. Explaining it in words is a bit tricky, so I'm kind of relying on the visualizer for this. We can just move this arrow over to D, and then C is no longer part of the list. So linked lists can be faster when inserting and deleting items from your collection, and linked lists also don't need to resize by copying all of the values to a new array. These are very strong advantages in favor of linked lists, but they are not downright better than arrays. So for example, if we wanted to access the last item in the linked list, we can't just jump straight there. We have to start from the start, which is A, and then we need to go next, 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 and then try to go next again, and because there is no next, that's how we know that this is the last item. That can be really slow. On the other hand, with an array, we can keep track of what values we have. So first of all, most languages will allow you to straight up get the size. It can tell you that there are 6 elements, so 6 minus 1 is 5, and access index 5, and that's the last value. But if the last few items are null, we can still keep track of how many items we've got using just a variable. If we have a population as well as the capacity, population as well as a capacity, we can just go to the last memory address, and we can do that a lot quicker than a linked list. We'll look at this in more detail when we cover big O notation, so that really allows us to see the difference in speed when performing these different operations. But it basically boils down to arrays are good for some things, dynamic arrays are good for other things, and linked lists are good for other things. One more thing about linked lists is what you can see in front of you right now is a depiction of a singly linked list. A singly linked list meaning that every node stores the value, so for example A, and the memory address of the next node. So B, maybe C, and D. There's also such thing as a doubly linked list, which you might come across. And a doubly linked list simply means that every node, as well as storing the memory address to the next node, also stores a memory address to the previous node. So in a singly linked list, if I have a reference to B, I can access C, because I just go to the memory address where the next item. I can do that because I have access to the next. I don't have access to A. I have access to A via the collection, but not via my reference to B. I could change that if I had a doubly linked list, because I would also have a previous memory address. This can be helpful because it allows you to traverse forwards and backwards, which is especially quite useful considering that you can't jump to a random point in the array quite quickly, or a random point in the collection like you can with an array. But it also means that you're storing more. In an array, you are pretty much storing just a little bit of metadata and then value, 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 value. With the linked list, you're storing value, memory address, value, memory address, and they might be in different places, and that might be useful, but you're storing more, and that's not always ideal. And by storing a previous, you are storing value, memory address, value, memory address, memory address. So you're storing more. And again, it depends on your situation to whether that is beneficial or not, but that is the trade-off that you'll need to consider. That's been the difference between static arrays, dynamic arrays, and linked lists. In the next video, we'll be talking about stacks and queues.